Well, anyway, thank you all for coming. I'm Rick W5RH. I've been a ham since 1969. Well, on and off since '69. I failed skydiving and motorcycle racing in between. But ever since I got back into ham radio in the mid to late '80s, I've been fascinated with antennas. And not that I'm a total expert on the subject. I just like to know how they work. I'm more leaning towards the empirical side. You know, I mean, I understand the theory and everything to a certain level, but I like the physical attributes and what you can do with the antennas and so forth. I've built lots of antennas, and EZNEC sort of goes into that frame. Again, I'm not an expert on EZNEC, but I've used it a whole lot for the antennas that I've built. You can do a whole lot more, but if you've never seen how it works, that's what I'm going to do tonight. And EZNEC is a PC-based application to design and test and troubleshoot antennas, and also learn about antennas. I mean, if you're trying to learn the basic theory and medium-level theories, it's good that you can demonstrate what you read in the books on a computer screen and see that that is actually true. For one example, if you have a center-fed dipole at a certain height, it may have a feed impedance of 70 ohms. But if you take that feed and move it out, as you move it out, that feed impedance increases out to like 400 ohms, or until you get to the end, it's a high impedance feed, so it's voltage fed, it's 1,000, 2,000 ohms. If you do that with an EZNEC, you can see that the changes in that impedance. So it's a good learning tool too. Why is it called? I call it EZNEC. Other people call it EZNEC. NEC is the NEC engine. It's numerical electromagnetics code. It's a method of moments antenna modeling. It's part of it came from population statistics, or the method came from population statistics. It's a way to estimate by breaking things down, and you'll see that it does break it down. They originally wrote at Lawrence Livermore in 1970. It's been improved. There's different versions of NEC now. I call it NEC, so I'll say EZNEC. I'm just going to stay with that. I may be totally wrong, but I've talked to Roy Llewellyn at Dayton. He calls it EZNEC. So if the guy that wrote it calls it EZNEC, I'll call it EZNEC. They're now up to version 4 in EZNEC, and version 4 is a pro version. It has to be licensed. You pay. If you're familiar with Jason Johnston, G0KSC, he runs OptiBeam. He has the low noise Yagis that he's building and all that stuff. He uses Pro 4. He pays $5,000 for his EZNEC license, but you can do an amazing amount of analysis with it. NEC is an engine that you can buy, you can download and use it on your own, but what Roy did was to put an interface to it. And the interface actually sets up the antennas, sets up the global attributes and so forth in the analysis. And he makes it easy, and that's what it is. You don't have to do any textual files or anything. It's all graphical with numbers in like a spreadsheet. He's got a few versions. The free version, okay, I'll tell you about that in a minute. He has a standard version, which is now up to version 6, and a professional version, which costs money to license it, because you have to buy the NEC license. So EZNEC, it's software by W7EL. He's got a web page. You can go out there, and he's got all types of information about it on his web page. I was going to print out some references and so forth, but because of my situation, I didn't have time. I have a sheet here, and I've got business cards, so if you'd like the reference sheet at the end of the presentation, just email me and I'll send it to you. Okay. NEC engine, nec2.org has all the information about the engine, the method of moments, and how that works. If you've read Krauss Antennas, not the 1950 version or revision of this book, but the 1988, he denotes about 50 pages to this method of antenna analysis. So I would suggest that if you calculus and differential equations, if you're familiar and easy with those, you'll love that book. Okay, this EZNEC has a free version. That's limited in what you can do, but you can buy the version and get a lot of segments and be able to analyze it. Some free programs, MMA and AGAL. It's written by two Germans and a Japanese ham. All are hams. It's free. And for NEC2, that's free. There's their website, and you just go to their website and download it. It's got an English version. It's all supported. It's I've used this probably 15 years ago just to see what it was like, but you know, it's different. Of course, it's got the same calculating engine in it. They all have the same NEC calculating engine in it, but the interface is different. You can do some different things with this. They all essentially do the same thing. There's the 4NE2, NEC2. That's their website. You can download that for free. And full versions, not a problem. So what I'm going to show you tonight is I'll just a brief, because we don't have much time, but it doesn't matter. Let's put it this way. I'll just show you the 20,000 foot view of EZNEC. Oh, we'll get into some antennas and so forth, but there is so much that this program does that I'm still learning. I'm still reading the manual. And the only time I read the manual is if I get to a specific thing or somebody asks me a question and I don't know the answer, then I'll go read it and find out about it. So I'm going to show you how to define an antenna, the wires, how they're defined, define the sources or the feed point, how you're driving it, what the power rating is, and so forth. There's some global definitions that have to take place. You have to know, are you in feet, you in wavelengths, you in meters, millimeters, what kind of plot do you want at? You want a 2D plot, you want an elevation, you want an azimuth, you want a 3D plot. Output characteristics, you want to view the antenna, what color do you want to make the currents on the display, and so forth. And then I'm going to show you the results, obviously, both graphic and numerical. Everything that is graphical is defined by numbers, tables, and you can have access to both. Okay, when you fire up EZNEC, this is the first screen. And show some of these. I mean, there's this list here is what antenna is it, what file is it, frequency, wavelength, wires. There's a couple of extra screens that come up, loads like coils or capacitors. You can define transmission lines, transformers, L networks. What type of ground? Do you want to be in free space? Do you be perfect ground, like a slate of infinite slate of gold, or you can be real ground. You can have wire loss. You can define any type of wire. There's the units, plot type, things like that. So those are the parameters that you have to set, and you have to fill in these in order to define an antenna. Over here, these are the results, the currents, because it shows you what the current is on the wires, the source data, that's the feed impedance, the load data, it shows you what's happening with these loads that you defined. SWR, this is a really cool tool, one of my favorites. You can do a SWR scan over any frequency range, and it shows you what's going on the antenna. So let's look at something. All right. So like I said, this is the first thing that you see. You got a file here. If you hit open, it goes to this. This comes with EZNEC. Like I said, I'm using the demo version of 6 because my purchased version of 5 would not run on here. It looks the same. There's some new things to it, but it's essentially the same. But they have backyard dipole, backyard V, quads.
Those are typical antennas that you already predefined, right?
Yeah, that he provides you.
Right.
This comes with it. And this is really good because you can go in and look at the 5-element Yagi and see how it's defined and what it does. And you can change that, you know. If you save it, then you ruin this file, but if you save it as something else, then this file stays the same. But okay, for example, backyard dipole frequencies, it's 20 meters. Of course, it tells you the wavelength. So let's go to wires. I mean, you're just using a dipole and some wires. How do we define those wires? All right. So on the wires, it's in a 3D space. You have X, you have Y, and you have Z. So that, and if you're in electronics, you remember that from along with right-hand rule and all that stuff. But that, X, Y, and Z. And that's how you define it. So if you see that says X in feet, this is 0, 0, 30. So it starts at X and Y 0, but it's 30 feet high because that's Z. And then it goes to X, stays in the X plane, but then it goes to 33.43 feet in the Y direction, and it's at 30 feet. So it's a 33.43 foot long dipole up at 30 feet. It uses number 12 wire. If you put a pound sign in front of that, it's a gauge. So if you put number 8, number 10, number 12, number 20, it already knows the size of that wire because it's a gauge. But you can put 2 inches, 3 inches, 4 inches for doing aluminum tubing. Anything you want. Segments, this is the method of moments. It breaks things down into segments, and those segments are what is calculated on in order to figure out what the antenna actually does. The demo versions limit you to 20 segments.
That's a lot.
And the other version, the version 5 that I bought has like 500 segments. But I wanted to find something this afternoon. I thought I wrote down about the segments. I guess I didn't.
Where are the segments based from? From center fed or from your
No,
viewpoint?
on this particular wire, which is that it breaks the antenna down into 11 segments. So if it's, for example, if it's 11 feet long, each segment would be a foot.
And you haven't defined the feed point yet.
Do I?
You have not defined the feed point yet.
I have not defined the feed point yet. So you know, I can change. There's 20 segments available. I can change that to 20. The insulation, you can define insulation on wire, but if you read the EZNEC manual, until you get to the pro version, the insulation makes very, very little difference in the calculations.
Rick, does the software pick the number of segments
No.
for you?
No,
You have to define it.
You define it.
Is there a strategy to define
Well,
it?
yes, there's a guideline. 10 segments per half wavelength for gain and pattern. But if you want real impedance or accurate impedance, it should be 20 segments minimum per half wavelength. That was what I found in the manual this afternoon. So, you know, and what happens is hopefully it'll come up as an error. What happens if your segments are too long, it tells you. If they're too short, it tells you. They have to be within a certain range. Now, it'll still work, it'll still calculate, but it doesn't calculate, it won't be as accurate as if it didn't have the error.
So how does that translate to a full wavelength dipole? If that's in a half wavelength?
Yeah, that's a half wavelength dipole. Just like
So
everybody
it's just
uses.
duplicated? It's just 2 on either side? 2 wires on either side from center fed if you do
No,
it center fed?
that's half wavelength. That
Okay, so
33
you just
feet,
pick
that's
So your
20
center fed
meters.
would be a quarter wavelength, just
Yeah, that's
on either
standard.
side.
No, it's a half.
Half quarter wave on each side of the center.
Yeah.
Standard dipole.
Well, we haven't defined where the center is yet, so let's do that. Okay, so this wires, you can, some antennas have a whole list of wires, that's why you can expand it out, so let's go down here. Okay, let's go to sources. This is the feed point.
Okay.
So where is the feed point? Well, we only have one wire, so we're gonna specify our first feed point on wire number 1, and we're gonna put it in the middle, 50%. Now, because of the way we've defined the segments, there's a rule. The feed point, the source, has to be in the middle of a segment. So if you have an odd number of segments, that puts right in the center, there's a segment, and you can put the feed point there. But if you have an even number of segments, the middle is at the junction of 2 segments, so it will move it off to the side like it has here to 47.5% of the length, which isn't much different than being in the center. And it shows you.
But you could fix that by going back and making the number of segments.
Yeah, I could put 19 in it,
Gotcha.
In fact, I'll just do that. Let's do that. See, that's the nice thing about it, you're not outside cutting wire. You're sitting at your desk and you're going, okay, I got
You're not
segments.
running your wire.
I'm gonna do 19, and then I'm gonna come back to sources, and we gotta go out of there and come back in there. 50%. See, right there, it put it at 50%, not 47.5, and it's in segment 10. Because segment 10 is in the middle. It's got 9 before it and 9 after, because we have 19. The type of source, there's voltage sources, there's current sources. Typically, you stay with a current source, because that's what center fed dipole will use. There's different reasons that you would use the voltage, or there's split feeds if you have 2 segments that come together at a 90-degree angle, things like that. And like I said, this thing can do a lot, but just for doing the basics is what I'm going to show you tonight. Phase. If you only have one source, you have 0 phase, but if you have 2 dipoles in phase, you have 4 verticals in phase, you have this, you can vary that phase. One source is 0, another source is 90 degrees, another antenna is 180 degrees, and it will drive them all equally with the amplitude and the same source, and you can define those sources, but you put the phases 0, then 90, then 180, or whatever you require for the antenna that you're working on. Okay. So loads, we're not going to get into loads, but that is the loads you actually define, again, like a source, where it is, what its actual position is, and a coil is a load, and it has a resistance typically and a reactance, because a load is, or when you're using a coil loaded antenna, it is canceling the capacitive reactance by having an inductive reactance, and that's where you define that. Now, how you find that out, that's up to you. You can use the handbook, use their charts, things like that, but there's some other methods you can use in this. Use an EZNEC to find out what those values could be. So, transmission lines. Transmission lines are virtual. They are just numbers. Transmission lines, all transmission lines, it can be calculated. They design transmission lines by figuring out what impedance and their losses and so forth and so on. And a transmission line with X lengths with an input impedance of Y has an output impedance of Z. It's math. So that's what this is. You don't see the transmission line on the diagram when you define something like that. Transformers, I've not messed with those. L networks, exactly what it says. L networks, you can put an L network at the input to a transmission line. So ground type, this is one of the things you really have to define. You can define free space. Put that dipole out in the middle of nowhere.
Which is not realistic, right?
Well, for VHF antennas, you put a 440 antenna up at 150 feet, you pretty much at free space, so.
But free space is really good for learning.
Yeah.
If you're comparing it against maybe a book that you've read, which they typically give free free space patterns and that kind of stuff, it's really a good, I think, a good tool for that.
Oh, wait a minute. Let's see. There's a free space pattern right there. It's a ball. Because you can see, here is you can see X right here. That's ground. X and Y are zero. This is 0. This is positive Z. This is minus Z. So it's in free space.
So where's the antenna in that?
Right dead center?
Right in the center along the X-axis, and that's one thing he may have done it in 6 and I haven't found it yet, but I would like him to put the antenna in there as a different color or something. When I do presentations on antenna types, I will show diagrams like this, but in PowerPoint I'll put a line in there that says, okay, here's who the antenna is and this is the radiation pattern. So,
Seems like the antenna ought to be on the y-axis, not the x-axis.
well, hang on.
Yeah,
Let's go back to
You said
Y.
lines where you-
Did I say X? I'm sorry.
Yeah.
You're right.
So it's along that y-axis.
You're right, it is.
Hey, yeah. Hey,
Okay.
if I make a
Otherwise, it'd
mistake,
be
let me know.
radiating off the ends by that polar, I mean, by the
Right.
chart.
Right. So,
Go back to that plot then.
so anyway, you want to go back to that plot?
Yeah, so it's along that center.
So it is along this line. I'm sorry. Thank you for pointing that out to me. It's a long day. Okay, the other thing you can do, this is a 3D plot, but you can also say, show the 2D plot, boom. Now, that's a 2D plot at 0 degrees. And you can do 0 degrees in free space because there's nothing there, but you can't do 0 degrees if there is real ground in there, because there's no radiation at 0 degrees. Well,
Well, how do you determine real ground?
hang on. And that's what we're getting to. So you got free space, you have perfect. Perfect is literally like having a sheet of whatever, aluminum, copper, gold.
At z equals 0, right?
Yeah, at 0. Yeah, Z equals 0. Real, again, this is real. You can use mini net, grounds, or high accuracy. I always use high accuracy because he used to, well, he still says it in the manual. If your computer's not fast enough, it doesn't matter what you have these days. Everything's fast enough. But on the DOS version, back in version 4, back 20 years ago, some of these calculations took a long time. But now things are pretty fast. And that's the nice thing about it. We're so used to having things instant. Web page up instant. This is do a Google search and having 20 things come up. Everything just boom, boom, boom. Once you get to know where all this stuff is and how to change it and everything, it's really easy to put models together. So let's do high accuracy, real ground. Now you can define what the ground is: Siemens per meter, dielectric constant, things like that. Depends on your area. Some people have great ground. Some people have, up in Nevada, may have terrible ground.
Now, how do you get a measurement of that? Where do you
How
go
do
to
you know
get
what you
that
got?
kind of measurement?
One of the places in the ARL handbook, they have a really coarse map on there that has contour lines that show you what that is, and you can use that, and you can see big differences. One of the cool things is, I don't know if y'all familiar with Team Vertical. The guys, it was Tom Schiller, N6BT. Yeah. Those guys years ago took verticals and they put them at the water's edge. And the reason they did that is because when they modeled the verticals at water's edge, they could get that bottom 1, 2, 3, 4 degrees of launch angle. Whereas if you put it over ground around here, you don't get anything until it's 5 or 6, 7 degrees. So they wanted that low angle. And it was cool, and you can see it if you would model a vertical and put it over ground like this. You can see that the pattern, there's space between ground and the actual radiation. But if you put perfect, like it would be beside salt water, it goes right down to that ground level. So, which goes to show you that the better the radial field, the better ground plane counterpoise that you have underneath the vertical does certainly help the radiation angle and obviously losses. So, one thing about EZNEC is, and one thing about antennas, you sort of need to know a little bit about antennas in order to use this. You can't just put numbers in. You've got to realize that, like Jerry was getting confused there on the length, you've got to realize that half wavelength on 20 meters is about 33 feet. And the impedance of that antenna, if center fed at half wavelength above the ground, is going to be about 70 ohms. If you put it higher, it's going to be less. If you put it lower, it's going to be less. That comes from studying a little bit of the theory of the antennas. So it's kind of a chicken and the egg situation. Do you learn about antennas first and then apply it to EZNEC, or use EZNEC to learn about antennas? You kind of have to do both at the same time. Let's see. Wire loss, you can see it's got copper, aluminum, tin, zinc, whatever. Doesn't have steel. Doesn't have steel fence wire. That's really lossy.
You still barbed wire in there?
Yeah. Now you can define your own. You know, you can measure what is barbed wire, about 3 ohms per foot, something like that. So anyway, I don't usually keep. It comes at 0, but I usually put. I use a lot of aluminum wire stolen from the electric company that when they leave wire at the end of the street. So here's units again: meters, millimeters, feet, inches, wavelengths, whatever you want to use, depending on what you're trying to do. Plot type, like I said, azimuth, elevation. Elevation is looking at it from the side. Well, I'll give you examples. So an azimuth plot. See, there's no sky wave at 0 elevation, and right here, the elevation angle, I have 0 degrees. Well, that's not good. So let's do 20 degrees. Okay. So this is plan view. This is looking at the top of the radiation pattern at 20 degrees angle. That's what it looks like, and there it is. The angle.
So as you change the degrees, the pattern changes.
Well, the pattern doesn't change, but the plot of the pattern changes.
Yeah, okay.
Because,
Like taking a slice through.
for example, if you go to elevation, this is from the side.
Right.
So here's the ground, and this is from the side, and then you can.
It's like Ken says, a slice of the pattern.
Yes, sir. Yes, sir. You're slicing it this way, depending on the elevation angle, or you're slicing it from the side.
So you're looking down the dipole right here.
That little dot in the center is the actual
Yeah.
line.
Well, this is. Oh, yeah. Now, hang on. I'm going to show you. You can move this dot around. See this down here? It says outer ring 7.03 dBi. Well, that's what that is at that point. It's 7 dBi, and the elevation is 36 degrees, right? So watch the gain and the elevation as I move it around.
Oh,
The elevation goes down, but the gain, and it's fast, you know. Okay, the other thing you can do is, on this, is you have a dipole, and you can view that dipole. Let's go up here. So you can see that it is in the Y, and you know, you can move this all around. You can zoom it, you can increase the current, increase the display of the current. You can move the image X, Y, and Z, and so forth. A couple of things. One of the neat things about EZNEC you can do is, hang on. Under view, you have objects. You have axes, and you have currents. Now, this purple is a current. Let me do something here. Let's keep that antenna. We're going to keep that, but it's 14 megahertz. So if I wanted, let's see, half second harmonic would be 28, third harmonic would be 42 megahertz, am I correct?
Yeah.
42. So let's do 42 megahertz. Don't change the antenna, don't rescale it, that's something else I'll show you. But let's just run the third harmonic on that same exact wire. See, there's a segmentation check warning that comes up. If I was really serious about this antenna, I'd dig into that. Okay.
Wow.
So that's fair enough. We changed the frequency. We've kept everything the same. We're going to view the antenna. Now, here's the cool thing. Now, everybody knows that on a multi-half wavelength dipole, that the current phase between each 180-degree section changes.
Yes.
One is positive, one's negative. Well, that's not what this shows. Well, EZNEC has this where I was before. I'm showing the currents, but right here, current phase. I don't know why he doesn't keep this turned on.
There you go.
There you go. That's exactly what it is. And it shows you, like, for every half wavelength, that standing wave current changes polarity. It's a good learning. So that's one of the cool things about that display, that you can change the phase. So let's go back here and go to 14. Okay. And we'll keep this 20-meter dipole, and we'll look at the plot of the standing wave ratio. Okay, so if the start frequency, let's say we'll go to 13 megahertz, and the stop frequency will go to 15 megahertz. Give it a pretty broad bandwidth. And the step in between will do, computers are fast, 0.05, and we'll say run. So it calculates for every point. It did a calculation, and you can see that here, SWR is 1.69 at that point. Okay.
And what's the frequency at that point?
Right there, frequency 14.4.
Okay.
Okay.
Already see it.
And there's the actual impedance, inflection coefficient, and deflection loss, whatever, return loss. Deflection loss. But you can see that this
I
dipole.
think it would make a difference here, the thickness of the wire, right?
Yeah, could be. Well, let's see. So
It gives you a
10
much
instead of
broader
12.
bandwidth.
yeah, okay. So let's go to wires.
Go to 10, 10 gauge instead of 12.
Get it. Okay, so instead of using number 12, how thick do you want to make it? Let's make it a 6
0,
inch.
0.
6 inch thick dipole.
6 inch thick.
Hey, let's.
Short pipe.
If you want to change something, let's go for broke, right?
Okay.
It's gonna be a rotatable dipole.
Okay.
Oh, obviously.
So we've run it,
Go back to that.
and
Shows the
okay.
curve.
That really doesn't show any difference. But if you come back here, and run it.
Oh, yeah, it's black,
Much more
longer
broad.
range.
There you go.
How big was that wire?
6
Big.
inches.
Is that radius or diameter?
So, diameter. So anyway, here, one of the things you can do with the sweep parameters is you can widen it out. I'm going from 4 megahertz to 30. It'll take a little bit to run, but it'll show you, if you have one of these end-fed wires that covers 8 bands, you can model that, and it'll actually show you where the...
This could be a camelback here, I think. Yeah.
Whoa.
So there's not a whole lot of difference.
It just goes stupid there.
That's why you need a tuner.
Yeah.
Absolutely.
Anyway, I'm surprised there isn't something.
So Rick, what is your reference for
Sorry.
SWR here? What impedance is your reference?
50 ohms, isn't it?
It is 50 ohms, but you can have an alternate of whatever you want.
Okay.
So whatever kind of cable you're hooking to a ladder line or whatever, like,
Well, that, or if you have some type of transformer, you have a 9-to-1 at the feed point, you can see what the 450 ohm standing wave ratio is. So,
Did you define a transmission line on that? I didn't notice if you did. Or are you looking at the
I'm-
SWR
we-
at the
we-
feed point?
That was virtual, right?
We are not looking at anything. We're looking at an antenna with a source.
So that's where
Feed
the
point.
SWR is, right there. at the
Right
feed
there,
point.
that's
Okay,
it,
okay.
that's it, that's it. Now, if you want to define a transmission line, you just have to say, okay, I have 100 feet of RG8. What's the impedance at the input? That's the only information
Can
you
you plot the SWR driving into that
So-
coax?
Yeah.
Well, the SWR will be the same. SWR doesn't change unless you have loss in the lines.
That's right.
Impedance changes, but the SWR
Impedance
doesn't
change. So what you want to do is, if you're trying to design for the lowest loss situation, is you want to have your feed impedance matching the characteristic impedance of the feed line. So if you have 50 ohm coax, you want 50 ohm, nominally 50 ohm. Nothing's right on the money. It's RF. Come on. You know? There's slop everywhere. Okay, so we did the SWR. This is pretty good. Well, yeah, you can run it again or not run it again, but I'm not going to run it again.
How do you show
Okay.
something like an inverted V?
Okay, just let me, one more thing, then I'll show you. Okay, over here, remember I said these were all the inputs and the global plotting display characteristics. Over here is the output. Source data. There's the actual, and on some of the plots you got this information at the bottom. But we're on the wire that you're analyzing, at the frequency you're using, and the source placement, that is the impedance. So it's resonant. I mean, it's minus J. If you read Siebeck, R.L. Siebeck, he wrote a whole bunch of antenna articles and actually did a course on this for the ARRL, which I'll talk about later. He said anything under plus or minus J10, he said is can be resonant, and it is. You know, it's like I said, there's lots of slop in RF. So there you go. It shows you the power, and there it is. That's what I was looking for, and I couldn't remember where it was. See that SWR 50 ohms, and then the alternate is 75. So okay, what else we got? Okay, so Jerry, you wanted to see
Yeah, inverted V,
another
say 80 meters.
So here we go. Open up. Go
You have to change
that
the wire,
number
too.
right there. Okay, so they have an inverted V, but I'm going to show it to you right here. Here it is. Now see, this is a split source because you can't put a source right at that point.
No,
You have you could do it one of two ways. You can put it off to the side, or you could use a split source. And he uses a split. It's a good example of a split source. And see what it says. See, it says SI. That's split current. So, but if you look at the wires on this, there are two wires.
yes.
All the wires that are in this thing need to be linear. They cannot bend. All the wire goes from here to here, here to here, here to here. If you need to do I'll show you how to generate a loop, but you generate a loop by putting a whole bunch of little straight lines. So
okay.
all the lines have to be orthogonal.
In other
Well,
words,
no,
you don't model.
that's the wrong-
you
that's
can't-
wrong.
In other words, you can't model a catenary.
No. Yeah, look, and I used the term orthogonal. That is not correct. The wires can be orthogonal, which is 90 degrees out, but they can be less than that. You can put wires anywhere. You cannot cross wires
They have to be tangent to your curve.
and keep them close.
They have to be tangent to your curve.
Yes, but you can't get within 1/1000th of a wavelength, I think, or 1/100th of a wavelength. You really need to put your wires farther apart than they are when you're designing things. You can't cross wires in this because it doesn't know that you're not. I don't want those connected, but you know.
What about this 20 segment limit per wavelength? You have a 20 segment per lambda limit?
Yeah, 20 segment per, well.
So now, if you're doing a piecewise linear approximation with a bunch of little pieces, doesn't the segment factor keep you from making your curve very high resolution?
That's why you spend $95 to get the one that increases your.
Standard, yeah, that's what I did.
You know, it's, you know, you can't, it's like, you can't get there from here. You owe me money.
So like the first piece is free and then.
You don't get a whole lot
So,
for free.
Again, I apologize for not being able to load my CD on here, but, anyway, so you can see, Jerry, that, that's 2 wires, okay?
Okay,
All right, so now, it's interesting because these wires are at an angle.
right.
So unless you've done your geometry homework before, and when I did tons of work with delta loops for years, trying to figure out a new way to do things, which I found, but you know, you had to figure out, do you have an isosceles triangle, right angle triangle, or whatever, and you could figure out the lengths beforehand. And then you could figure out the X, Y, Z points.
So you just get out some graph paper.
You
and
get
draw
out
what you
graph
want, then
paper
you
and
derive
draw.
your X, Y list.
Because right now, well, here, because these are at an angle, you don't know how long these wires are. But if you run the plot, and then you go back to the view antenna, once you run it, go back to the view antenna. Oh good, I'm gonna,
Whoops.
come on, hang on. Wire numbers, yeah. Where's,
You still got that 6-inch pipe?
no, no. Oh, this is 6. See, in 5, when I select 2 or 1, oh, wait, sorry. I'm getting ahead of myself. If I go to wires and select 1, is that gonna do it for me? No.
No.
On my version, if you select a wire in the wires, it comes down here and it says wire 1 is 26 feet long. Wire, and you select wire 2 and it says wires 2. That's gotta be somewhere, but again, this is the new version. I'm sorry, I don't know where it is. But that's how you figure out if you have a line that is not on a vertical or a horizontal. You can figure out how long it is by.
So it'll actually tell you, depending on the angle, so if you've got your antenna as an inverted VC, you've got antenna up to 40 feet, and your ends are 20 feet,
Yep.
would it tell you exactly how long you need to have your wires?
Well, you just model it. If this point is 40 feet and this point is 20 feet, then you know you got to know how far out. How far out is it?
Okay.
So that's why I said for some antennas, you really need to sit down with a piece of graph paper and draw this stuff out. So, but anyway, let me see. So we do far field plot. Oh, we already did that.
Wow.
So you could, you know, compare that to the dipole and so forth.
It's gonna be pretty
Let
steep.
me show you some other antennas that he has in here. I have all types of antennas that are on my home computer. He's got a WHAK. Nobody knows what one of those is. Let's just look at it. But it's just 2 dipoles in now. Let's see, how did they do that? See, they've got them 180 degrees out of phase.
Yes.
See that? So. Okay, let's see what other antenna. He does have a Yagi. It's an MBS Yagi. That's only got 3 elements, but let's look at it. So, there you go.
That's on the ground.
So he's got, and 1, that's not a source, but this is, that's 1, 2, 3 source. So, So anything you can pretty much visualize, you can model.
If that's a Yagi, why does it have multiple sources? Because
It
they're gonna be parasitic.
It doesn't, that's 000. I bet you, well,
Oh.
before I say it doesn't have multiple sources, I'm gonna come here and see, it only has one source, and that's on wire 2. So that's the driven.
Driven reflector and director.
And then if you look at the wires here, just make that up. So wire 1 is the reflector at 57.5 inches. And it's 54, well, no, that's height, sorry. No, it's not, that's length.
That's the line, that's right.
Yeah, it goes from minus 57.5 to 57.5, so it's straddling the x-axis. So. And it's 1/2 inch in diameter, 11 segments on each. Now I can't model this one because it's 33 segments, and if I say I want a plot of that, sorry, dude, you owe me $95.
Exceeded your segment limit.
Sorry.
Is that a one-time fee?
Yes.
Yeah, I think.
Yeah, it's a one-time fee, and what he sends you is you can get it downloaded. I bought it from Dayton, so he gave me a CD, which now has a virus on it for some reason. But you download it, and it's unlicensed, so you can give it to all your friends, much to Roy's displeasure. You know, and the FBI will be on your doorstep the next day, but it's unlicensed. I mean, he talks about that. He says it costs him more money to put in licensing. He says he'll just, pretty much all hands
So
are
why would the FBI be on you? If it's unlicensed,
Because
it
you're
doesn't
stealing.
make any difference. You're not stealing it,
Yeah, you are. Yeah, you
not a copyright.
are. Anyway,
But it isn't copyrighted.
okay. So we look at everything there. There are a couple of things I want to show you on the wires menu. Let's I gotta find. Looking for a vertical.
Don't get no respect.
Here we go. So if we go to, great, come on, wires menu. There's a create tool. You need to watch this.
I know, that's why I'm getting closer.
Okay, create, there's a couple of things you can do, but since you're moved up, radials. You can generate, okay, this is a first group, last group, total number of radials, but if you want to put in, if you want to put in 36,
Yes.
okay. Oh, sorry, first wire in the group, sorry. It has just generated 36 radials, all the same, just by doing that simple thing. Okay, so I come over here, there it is.
And they're all 10 degrees apart.
Very cool.
And how high are they above the ground?
They are above the ground. That is a restriction on the NEC2 engine. They cannot be touching the ground.
Okay.
You know.
But it takes care of that. Do I have to
It-
set the
it-
elevation?
Yes, it will take care of that. Now, you should go in and specify it at a certain height, but he mentions in the user manual that, in order to model buried radials, that just putting them above the ground is close enough. Roy's the one that wrote the QEX articles about grounding and raised radials and all that last year before. Yeah, so but any radial field you want to do, I mean, do whatever you need. It's pretty cool. Saves a whole lot of time. All right, so if you're into quads, let's go back to wires again.
So show us the vertical pattern on that, or the pattern,
Well, before I
Yeah.
kill it. Oh, one or more wires are duplicates.
Doesn't like it.
It's probably number 2.
Why doesn't it like it? Oh. So, the other thing is that, okay, this is a spreadsheet of the wires, but you can add wires, delete them, move them, group modify. If a group modify is, you can highlight all of them and change their height above ground. You can highlight all of them and change them to number 12 wire. You can highlight 6 of them and change an attribute. That's what group modify.
How much gain do you get by doing something like that? I mean, is it labor intensive to do that, and how much do you gain by doing it?
Well, I mean, is it labor intensive? How long did that take me to generate that? 30
Yeah, but I mean
seconds?
to actually do it.
Oh,
But that's why-
real
that's-
world radials?
That's why you're modeling. So you don't have to put 36 radials out and go measure like Jerry Seevick did years and years and years ago. You know, that's the way they had to do it, so.
But in the
Or,
real
So just
world,
delete those last 2 lines?
it makes a big difference.
Yeah.
How in your efficiency, how many radials you have. And how much power actually gets radiated versus how much power gets lost.
and you can show that
That's right.
in this program. If you do, oh, I didn't get all of them, sorry.
Just heat up the earth wire.
If you do this correctly,
Heat it for
you know, and pay attention to it and so, pay attention to it and put it in the right freaking numbers. Why do I keep putting 9? Now I can do it, right?
Yeah. No?
Oh, segments, sorry, can't do it. Sorry. But if you pay attention to this and model things, and one of the cool things is which I read about in version 6, you know, in the back of the AORL handbook, they have a CD.
Yeah.
On that CD are model antennas, and you can, in this demo version, there's a special version of this demo version that has all of those models in there. I was doing some research on direct fed Yagis, 50 ohm Yagis. That seems to be the big thing. Nobody's using gamma matches or anything anymore. I shouldn't say nobody, but most people don't. They're all direct feed. You get less gain and less front to back, but the overall gain is better. Anyway, Tom has a whole bunch of defined Yagis, 3 element, 4 element, 5 element, 6 element for 20 meters, then he goes to 17, 12 and all that. And you punch in these numbers exactly like that into EZNEC, and it comes out right on the money. Direct feed, 50 ohms, wide SWR bandwidth. It's pretty cool. So, but that's how they got there. They use this as the analyzing. There's another tool that adds to EZNEC, which I'll show you. I'll show you where it is and sort of what it does after we get through this. Okay, I know we're getting on 8:30. Sorry. What was I going to show you? Wires. Let's go delete 1 to 37. Okay. There we go. Wires. Create. We did the radials. Let's do the loop. You can actually generate. I did some work for Purple Zebra. You know, anybody know Dale KC2PZ? He built some round quad elements years ago, and he said, "How do I model those?" I said, "Tell me how big they are, and I'll model them for you." So I did, and it was a learning experience for me, but it was fun. But you could see this. You can say the circumference is so much, and define the actual loop, and let's see, signals per side. Say the number of sides 4. Okay, so let's just do this, and then we'll view the antenna. So there we go. There's a quad, right?
That's one, but if you got more than one,
Understand? So
That does
let's
isn't
go back to the
impressive.
wires menu and do create loop. The number of sides. What if he had a round loop? So we're gonna, you gotta use straight lines. So let's use 40 sides. Okay. And then we go back to view the antenna. There you go. It's 40 individual lines that generates that circular loop. You know how long it took me to do that the first time I did that? About 15 years ago? A long time. And then I got online and found out somebody had done all that work before.
So is the angle between each segment, I mean, I can't see it here, is it 90 degrees or what is it?
Hang on.
Or is it depending upon how many there are?
It's 180.
Right there.
860 degrees divided by 40.
Yeah.
Yeah.
Okay.
Yeah. So each line is straight, but it tilts a little bit with each one. So,
Let's see, for him to be.
you know, and you can, I mean,
9
with the paid version, I mean, you can have 120 of these. You get 360 of them. You know, so, but it's just these really cool tools that if you're dealing with quads and so forth, that you can easily do it. Let's go back to wires again. I don't know.
Does somebody have a model of the hex beam on the, or EZNEC
yeah.
on the internet somewhere?
They've got models of everything on
So there's
there.
a
You
library
just-
somewhere where you can get that stuff, or you just have to?
I've never
look it
found a
up?
library, but I've just found people that have done it.
So you just Google
Because
that?
they'll write a blog about it, and they'll say, okay, here's the EZNEC file,
Oh, okay.
and, you know.
If you post a question like that on some of these
Well, there you go.
antenna
That's another
reflectors,
way.
somebody will say, well, old Bill's got one, you know, go see his website. And you go over there and you'll see, and you'll have a table or a listing or something. And you just have to, you know, understand that it may or may not be right.
Yeah.
Let me start with,
So if I can go back here,
Remember when it's work, what you
do a four-sided loop. And then Jerry, you asked me, you only had one. I'm not doing this right.
First thing about quads is they're
Wire,
very quiet.
copy wires. First wire to copy 2, last to copy. Okay, now here's the deal. The 2, 3, 4, and 5 are the four-sided loop. They're at a certain location.
Right.
If I want to put another one of those,
Oh,
I can, and here I'm doing it.
Oh,
Do I
okay.
want to offset it on X, Y, or Z? So what I'm going to do is
Why?
let's offset it on Y by 30 inches, for example.
Okay.
Boom. So it puts those at 30 inches, and then we're going to come back here, and I'm going to show you what it did.
Yes, it
I
has.
don't want to do that. Well,
Didn't do it.
I think my scale is way off, sorry. No. Oh, there you go. You can see the two loops. I
You should have done it in X.
I should have done it in X, yes, exactly right. So let's do that. So back to wires. Can I
what from this use that for again?
group modify? Well, you know what I'm going to do? Let's do this 2, 3, 4, 5. Kill those wires. 6. Okay. Okay. Let's do it again. No. Wire. Copy 2 through 5, and you said X.
Right, that's
So let's do
30 inches of that.
60 inches. Okay. There it is. Okay.
So what's your gain over 1 versus 2?
Well, we're
That's too close
what
together.
you know. We're just demonstrating a capability. We're not really going for gain.
Oh, okay.
But as far as close space wires and loops, the original quad loop was, what was his name, Clarence Moore, down at HCJB. When he applied for his patent back in 1930 or 39 or something like that, was not a single wire, it was 2 wires. And the difference between a single wire loop and a 2-wire loop is just feed impedance, just like a folded dipole. Doesn't do anything for gain or anything. Anyway, so that is scratching the surface of EZNEC. Is there anything that anybody would like to see the capability of? If I can, I will. If I can't, I'll tell you I don't.
Say, I've got a question for you.
Sir?
You said you had another program that's sort of,
Another program?
yeah, another one that works with this? Maybe I misunderstood.
Oh, yeah. Once we get through with this, I'll show
Okay, I
you.
just want to keep this.
Oh, okay.
If you've got an inverted V, and say it's at 40 feet, and you got 20 feet at each end, and you got a tree next to it, and it's over a house, and there's a tree on the other side, is there a way to tell how that affects the radiation pattern?
Not exactly,
Okay, but that's the answer.
but because you cannot model trees, people in like the antenna compendium and stuff have modeled cars, but it's wireframe modeling. They just sort of wire the outline. You just have to give a reasonable representation. You can't do that for a house or a car.
Just a couple months ago, yeah.
So,
Really, really.
Yeah, that's right.
plus 2 months ago in QST, there's an article about green leaves.
Trees, yeah, that's why I was wondering if you could
What time
model.
of year is it? Where's the?
That wasn't model, though, that was empirical, wasn't it?
Yeah, that,
Yeah.
you're right.
Yeah, that was empirical.
Okay, go back to finish up here.
There's so much you can do with those.
Oh, there it is. Okay, some additional information. If you want to, if you've used EZNEC before, you probably know all this. I probably know more than I do. And I hope you do. Couple of places. The ARL book, like I said, has that special EZNEC Demo that has all their stuff in it. The EZNEC manual. The EZNEC manual. Roy does a tremendous job of giving you examples and so forth.
No, I've got one, I just,
Anyway, I put most of my stuff on Kindle and then download the PDFs to my iPad and keep it on there. There's been QST articles about antenna modeling. Ward Silver wrote some, and a few other people. CBIC wrote a couple of articles. One, that may not have been, it was in the Antenna Compendium, in Introduction. I have all 8 of these. They're pretty good. CBIC wrote the Antenna Compendium thing. He wrote some articles about modeling too. There's a history of modeling in the Antenna Compendium. Ancillary programs, that's one thing I wanted to tell you about, was AC6LA, Dan McGuire. If you're familiar with a program called TL Details, I've been talking about TL Details for 20 years. It's the best transmission line program in relationship to TLW, which comes in the ARL handbook. That's pretty good too. It does some things TL Details doesn't, but TL Details does some stuff that TLW doesn't. But he wrote that. But he wrote this Auto EZ, and what that does, it allows you to put a spreadsheet together of all of the characteristics of an antenna, the tubing size, the length, the spacing, the this, the that, and it allows you to input that into EZNEC as an iterative process. I'm going to use A1, B1, C1 for this result. Then I'm going to use A1, B1, C2 for the next result. And then it just goes down each column. So however many you have in A1, B, and C, it has that many results. And that's how Jason Johnson, this guy, Jason Johnson, OptiBeam UK, he had a couple of interviews in NCJ, with Ward Silver, and he was talking about how he designs his antennas, and that's how he does it. They just iterate the crap out of all
Over
the
the top.
characteristics, and he gets down to that gnat's ass, and it works. It's beautiful. But that's the one I was talking about. So,
So that's how you do optimizing.
yeah, he uses something, it's an optimizing mathematic process, but I can't remember the name of it. But it costs him like $5,000 to do it or something like that. It's crazy.
Okay, I had a conversation like 15 years ago with
Yeah.
some guy. He said at that time, the only modeling software that did optimization was YO and AO.
Yes, with
And
Craig
I still
Beasley.
use it, and I
Uh-huh.
see this, and I go, use YO and AO even though it's DOS.
Yeah, one of the things about quote optimizing, no, it was efficiency. Sorry, a friend of mine had a package. I can't remember what he was using, but they had this thing called, or they had a characteristic antenna efficiency. And when he was looking for a new package, he was talking about EZNEC with me, and I said, "Oh, EZNEC's great." He says, "Well, how do you get where's the efficiency tag?" There isn't any efficiency tag in EZNEC. Oh, well, this program has it. I said, to do efficiency, you have to put everything to lossless, run it, and then put everything to realistic and run it, and look at the difference. And that's how you get. And even Roy says that in the manual. So, okay, this is the page. I mean, if you're interested in getting this, I've got some business cards and stuff. But send me an email. And it just shows you the websites and stuff like that. Sorry I didn't get that printed out, but there's all types of stuff on modeling. Just like there's all types of stuff on antennas themselves. I'm not sure, and I'll do the commercial on this. Continued Education, ARRL came out with the antenna modeling course for EZNEC and NEC Win, and they did them both in the same book at the same time, and it was really confusing. So I bought the course anyway. It was $39 for the book, and then so much for, and all the online thing did was keep track of what you were doing. It didn't do anything. And then they had mentors, and the first question I asked the mentor, he couldn't get an answer to. So I wrote ARL, and I said, look, you got to change this course. Choose your poison. Choose EZNEC or choose something, but don't do both. I mean, CNEC's pretty smart, but I don't know why they did that. Anyway, the best thing to do if you're going to take that course, yeah, they give you a bunch of sample antennas and so forth, but the best thing is just email me and I'll send you the manual, and just go through the manual. So. Anyway, that's all I think that's all I got. Oh, here's an advertisement. I write a monthly column in the Big Mark newsletter,
Yes.
The Beacon, called The Radio Hotel, and it's all about antenna systems, transmission lines, matching networks. It's a one-pager, and what I'm trying to do is get people to not only read what I write, but I try to lead them to, hey, these websites have the information about the antenna you're interested in, or back in QST 50 years ago, they had a hex beam. They really did. Yeah, and just like I said, antennas are an interest to me, and this is a general column. But from that, I've got no more.
All right, excellent.
So
Very good. Save it as something else, right? So then that builds my little models without having to do, what I do as little work as possible.
Yeah.
But it helps you, it's things like looking how the impedance of an antenna changes as you move it above ground. Take the 20-meter dipole, put it at 15 feet and see what it said. Put it at 30 feet, put it at 45 feet, and you'll be surprised what kind of things you can learn. Then if you go back and read the antenna book, they got the graph of that stuff, and it says heights and wavelength above the ground, and it's just uncanny. It makes that graph meaningful now. Where before it was kind of mystic, but tinkering with that, it really made a big difference.
well, the thing about that, the thing that gets me is that graph was done back in the 20s
Yeah.
and 30s.
Yeah.
And it's still fairly accurate.
On pre-slide rule paper and pencil calculation. Can you,
Wow.
and
No
here's-
slip, no slip.
thing.
That's
That's why I like TL details. I don't need a Smith chart, I just use TL details. I can find out exactly what I want.
We didn't have a